The most durable engines ever mass-produced came out of Japan in the 80s and 90s. Million-mile 4-cylinders. Iron block 6s that outlived the cars around them. The engineers who built them are still publishing papers. And if you actually read those papers, the message is blunt. Modern engines were not designed to last longer. They were designed to trade lifespan for something else, on purpose. To understand what changed, you have to understand what a Japanese engine from that era actually was. Take the Toyota 22RE, a 2.4-liter 4-cylinder that went into pickups and 4Runners starting in the early 80s. Cast iron block, single overhead cam, simple electronic fuel injection. It made around 100 horsepower, which was nothing special even then. Mechanics started calling it the million-mile engine, and they weren't joking. Trucks with these engines survived decades of agricultural abuse on nothing but oil changes and spark plugs. The valve train was so simple, there was almost nothing in it that could fail in an interesting way. Or take the 2JZ, a 3-liter inline-6 Toyota introduced in the early 90s. Closed deck iron block, forged steel crankshaft, in naturally aspirated form. It made around 220 horsepower. The block could handle more than 1,000. Teardowns of examples with over 400,000 miles show internals that look barely broken in. Toyota built the naturally aspirated version and the twin turbo version with the same bones, which means the everyday sedan engine was engineered to survive stresses it would never see in its entire service life. Honda was doing the same thing with its 4s. Nissan was doing it with the straight 6 in the Skyline. Across the industry, the quiet rule was the same. Build the hardware for the worst case, then sell it tuned for the average case. That was the pattern. Japanese manufacturers in that era tuned engines to a fraction of what the metal could take. A component that needed to survive 100,000 miles was built to survive 300,000. Engineers call it margin. Everyone else calls it overbuilding. Whatever you call it. It's why a 90s Camry with cracked paint and 250,000 miles still starts on the first crank. Here's the thing though, margin is expensive, margin is heavy, and margin burns fuel. An engine loafing along at a third of its structural capacity is hauling around iron and bearing surface it almost never uses. Through the 80s and 90s, nobody cared. Gas was cheap. Emissions rules were manageable. The extra metal was a rounding error on the fuel bill. It also wasn't an accident of culture. It was policy. Toyota's whole production philosophy, built in the post-war years, treated every defect as a wound and every proven design as an asset you improve slowly, instead of replacing loudly. Japanese firms in that era were famous for letting competitors debut a new technology, watching it fail in someone else's showroom, and adopting it only after the sharp edges were filed off. Being last to market with a feature was considered a strength. And through the bubble economy of the late 80s, the money was there to indulge all of it. Iron blocks, forged cranks, hand-checked tolerances, engineering budgets that would embarrass a defense contractor. Then the rules changed, and the engines changed with them. The problem landed on every engine designer's desk at roughly the same time, and it looked like this. Regulators in the US, Europe, and Japan began ratcheting fuel economy and carbon dioxide targets tighter every few years. Corporate average fuel economy standards in America, the Euro standards on the other side of the Atlantic, each generation stricter than the last. Japan's own efficiency mandates miss the targets, and you pay fines, lose fleet credits, or lose the right to sell cars in entire markets. The targets didn't care how you got there. They just kept moving. And here's the trap. Customers were not asking for slower cars. They wanted more power, more towing, more features in vehicles that kept getting heavier every generation because of safety structure and equipment. So the assignment handed to every powertrain department on Earth was more power, less fuel, fewer emissions, same price. Pick all four. There is no free way to do that. Physics doesn't hand out efficiency for nothing. Every percentage point of fuel economy had to come from somewhere, and the somewhere over and over turned out to be the quiet reserves the old engines carried. The margin, the overbuilding, the stuff that made a 22RE boring and immortal. Modern engine design became a controlled demolition of everything that made old engines last, executed by very smart people who knew exactly what they were removing. That last part matters. This wasn't incompetence. It was arithmetic performed under legal deadline. Start with displacement, because that's where the industry started. The fastest paper route to better fuel economy is a smaller engine. Less metal moving, less friction, less pumping loss at light load. Problem: a small engine makes small power. Solution: bolt on a turbocharger and stuff the cylinders with compressed air whenever the driver asks for more. The industry called it downsizing, and by the 2010s it was everywhere. Ford replaced full-size truck V8s with twin-turbo V6s and put a 1-liter 3-cylinder into family hatchbacks, an engine small enough to sit on a desk, replacing 3 larger engines from the previous generation. Entire European model lines ran on tiny turbocharged 3s, making the power of yesterday's 2.5-liter engines. On the government test cycle, it worked beautifully. The test cycles were gentle, and a small engine barely touching its turbo sips fuel. In the real world, drivers found the boost immediately and used it constantly, which is where the joke came from. You can have eco or you can have boost, but you can't have both. And under boost, a tiny engine runs cylinder pressures and temperatures the old, naturally aspirated engines never saw on their worst day. One engineering writer put it plainly: the engines got smaller, but they work exponentially harder. A 3-cylinder hauling a crossover up an on-ramp is a small athlete sprinting with a piano on its back. It can do it. The question was always how many times. Here's the detail that gives the game away. After the diesel emissions scandal, European regulators moved from laboratory test cycles toward real-world, on-road testing. And the moment the tests started resembling actual driving, several manufacturers quietly began making their engines bigger again, because the tiny turbos that aced the lab were running rich and dirty on real roads. The downsizing wave wasn't optimized for your driveway. It was optimized for a test protocol, and when the protocol changed, so did the engineering. That should tell you exactly who these engines were really designed for. The turbo itself brought its own bill. A turbocharger spins at over 100,000 revolutions per minute, glowing hot, lubricated and cooled by the same engine oil that does everything else. Shut a hot turbo down carelessly and the oil inside it can cook into deposits. Let the seals age and it breathes oil into the intake. Every turbocharged engine carries a small, fast, furiously hot machine bolted to its side, and that machine has to survive as long as the engine does for the engine to be called reliable. Then came the fuel system. Port injection, the old method, sprayed fuel onto the back of the intake valves, where it mixed with air on the way in. Direct injection sprays it straight into the cylinder at enormous pressure, timed to the microsecond. That gives precise control, allows higher compression ratios, and buys real, measurable efficiency. It also created a problem nobody put in the brochure. With port injection, gasoline constantly washed the intake valves clean, like a self-rinsing system nobody had to design because it came free. With direct injection, the valves never see fuel. Oil vapors from the crankcase ventilation system bake onto the backs of the valves, layer after layer, like creosote in a chimney. Carbon buildup, rough, idle misfires, lost power, and on some engines a walnut shell blasting session every so often just so the engine can breathe properly. Direct injection also introduced low-speed pre-ignition, a phenomenon where fuel and oil residue ignites early under high load at low revs and hammers pistons hard enough to crack them. The industry had to reformulate engine oils specifically to make this stop happening, and the plumbing itself became a liability. Direct injection needs fuel at pressures dozens of times higher than the old port systems, which means a mechanical high-pressure pump, usually driven off a camshaft lobe, hammering away for the life of the engine. Early German designs wore the pump followers and the cam lobes that drove them. Injector tips, now living inside the combustion chamber itself, coke up with deposits and start spraying badly, which hurts power, mileage, and in extreme cases melts holes in pistons. Under port injection, the fuel system was a set of cheap plastic squirters that basically never failed. Under direct injection, it's a precision hydraulic system operating in fire. Toyota's engineers saw the valve problem coming, by the way. Their D4S system runs both port injectors and direct injectors on the same engine, using the port injectors partly to keep the valves washed. That's a Japanese company paying for two complete fuel systems on one engine because it didn't fully trust one. Remember that? It's a theme. Next, the oil. This is where the Japanese fingerprints are all over the reveal. For decades, engines ran oil with the consistency of syrup. 10W30, 5W30. A thick, forgiving cushion between metal parts. But thick oil creates drag, and drag burns fuel. So Japanese automakers, chasing every 0.1%, began pushing viscosity down. 0W20, then 0W16, which Japanese manufacturers were factory filling in their home market by 2009, years before the rest of the world had even heard of it. Then, the Japanese industry built an entirely new oil specification called JASO GLV1, released in 2019, to standardize 0W8, an oil closer to water than to the stuff your father poured into his truck. And here's the part almost nobody reads. The technical papers behind these oils, written by engineers at Nissan and Toyota and their partners, state the trade openly. One development paper on 0W8 says, in nearly these words, that lower viscosity oil generally has negative aspects with regard to oil consumption and anti-wear performance. That's the reveal. Not a leak, not a whistleblower. A published technical paper from the Society of Automotive Engineers, written by the people who developed the oil. They wrote down that thinner oil protects less, then explained the chemistry they used to claw some of that protection back. Molybdenum friction modifiers and film forming additives standing in for the physical cushion that used to just be there. The measured gain for going from 0W16 all the way down to 0W8, about 0.8% fuel economy, under 1%. That's how hard the industry was scraping the bottom of the barrel by the end. Entire specifications, entire chemistry programs for less than a single percent. So that's the shape of the story. Regulations squeezed. Engineers responded with smaller engines working harder, hotter combustion, thinner oil, and tolerances measured in microns. Every move was rational. Every move was documented in the open literature. And every move spent a little of the margin that used to be your engine's retirement fund. And that's before we even get to the part where somebody decided to run a rubber timing belt swimming in engine oil. If you're finding this useful, hit subscribe. We do one of these deep dives every week. All right, back to it. Let's get into the rest of the hardware, because the details are where the trade-offs stop being abstract and start being invoices. Piston rings first. The rings seal combustion above the piston and scrape oil off the cylinder wall below it. For a century, they were relatively wide and pressed firmly outward against the bore. That firm contact causes friction, and ring friction is a meaningful slice of an engine's total internal drag. So modern engines across the whole industry moved to low-tension rings, thinner, lighter, pressing against the wall with a fraction of the old force. Compare the ring pack from an 80s Toyota to a current one, and the difference is visible from across the room. Race engine builders had used low-tension rings for years, and they'd tell you the deal's straight, less friction and more power, in exchange for more oil consumption and shorter ring life. That was a fine trade in a race engine rebuilt every season. Now it's in your commuter car, scheduled for its next oil change in 10,000 miles. Low-tension rings have a specific failure pattern. With so little spring force, they can't push back against carbon deposits forming in their grooves. Deposits build, rings stick, sealing fails, And now combustion gases blow down into the crankcase, while oil sneaks up into the cylinders and burns, which creates more deposits, which sticks the rings further. It's a slow spiral, and direct injection feeds it, because fuel washing down the cylinder walls dilutes the oil and accelerates the whole cycle. Several manufacturers spent the 2010s explaining to unhappy customers that burning a quart of oil every 1,000 miles or so was within normal operating parameters. On engines from the old era, burning oil like that meant something was broken. On some engines from the new era, it meant everything was working exactly as designed. To understand why any of this matters, you need one piece of physics. A crankshaft bearing doesn't actually touch its journal when the engine runs. The spinning shaft drags oil into the gap and rides on a pressurized wedge of it, a film thinner than a human hair, and as long as that film exists, wear is nearly zero. That's why old engines could run practically forever. The metal never met. Everything about film strength depends on viscosity, clearance, load, and temperature. Thin the oil, tighten the clearance, raise the load with a turbo, and raise the temperature with hotter combustion, and you've attacked the film from all four directions at once. The film still holds on paper, with margin calculated by simulation instead of guessed with a safety factor. The difference is that when the old engineers guessed, they guessed fat. Now combine that with the thin oil. A 0W8 film in a modern engine is microns thick, flowing through bearing clearances machined tighter than anything the old factories could hold. Toyota's newest engines have oil passages and clearances designed around oil that thin. And when everything is perfect, it works, and the engineering is genuinely elegant. But the system has almost no tolerance for anything being imperfect. Old thick oil could hold a little grit in suspension, cushion a slightly worn bearing, survive an owner who stretched the change interval. The new system is a high wire act. The wire is thinner, the safety net is gone, and the maintenance schedule says, walk it every day for 15 years. Which brings us to the wet belt, possibly the single most self-defeating idea of the entire era. Timing belts traditionally ran dry outside the engine behind a plastic cover where oil couldn't attack the rubber. Timing chains ran inside the engine, bathed in oil, and lasted longer but cost more friction and more noise. Around 2007, engineers found a compromise. Run a toothed rubber belt inside the engine, immersed in oil. Oil has a lower friction coefficient than dry rubber on a pulley, so the belt in oil design was worth about 2.5% in fuel consumption against a conventional setup. Quieter than a chain, more efficient than a dry belt. Ford put it in the EcoBoost family. The parent company of Peugeot and Citroën put it in the PureTech. In the United Kingdom alone, over 700,000 vehicles ended up running Ford's small petrol engine with a wet belt. The belts and the oils were supposedly formulated for each other. In the real world, extended service intervals, short trips that never warmed the oil, and fills that didn't exactly match spec broke the rubber down anyway. And a wet belt fails in a uniquely vicious way. It doesn't just snap like a dry belt, it sheds. Rubber crumbs drift through the oil system and pack into the pickup strainer, the single small screen through which every drop of the engine's oil supply must pass. The strainer clogs, oil pressure collapses, and an engine can seize within seconds while having shown no symptoms the day before. Some owners learned to unscrew the oil filler cap and inspect a visible section of belt with a flashlight, like checking a smoke detector. Replacement intervals that started at 10 years or 150,000 miles got slashed, on some engines to 6 years or around 60,000. The parent company of Peugeot eventually extended warranties up to 10 years and opened a compensation portal for affected owners. Real-world failure data settled around depressingly ordinary mileages, often between 50 and 100,000 miles. Squarely in second owner territory, the people least likely to know the belt existed. And the ending tells you the verdict the industry reached about its own idea. The newest versions of these engines quietly went back to timing chains. all of it. Every seized engine and every compensation claim purchased for roughly 2.5%. Add the smaller stuff, and the pattern gets denser. Start-stop systems that shut the engine off at every red light, multiplying start cycles into the hundreds of thousands over a car's life. Each restart, a brief moment of marginal lubrication that the fuel economy test rewards and the crankshaft bearings remember. Compression ratios push to 13 and 14 to 1, which extracts more work from every drop of fuel and leaves less headroom for bad gas and hot days. Cylinder deactivation, adding hydraulic complexity deep inside the valve train. Exhaust gas recirculation loops feeding soot back through the intake. Every single feature earns its keep on the regulatory test cycle. Every single one adds a failure mode the old engines simply didn't have, or spends margin the old engines kept in reserve. None of this stayed theoretical. The bill came due in public, in courtrooms, and recall notices, and it did not spare anyone. Not even the companies that invented reliability. Hyundai and Kia went first and went hardest. Their Theta 2 4-cylinder, a modern direct injection design spread across millions of Sonatas, Optimas, Sorrentos, and Santa Fe's, began seizing and in some cases catching fire. The core issue was manufacturing debris restricting oil flow to the connecting rod bearings, and the tight, hot, thin oiled architecture had no forgiveness for it. The fallout ran for the better part of a decade. Recalls, record federal penalties, and class action settlements ultimately valued in the billions of dollars, with extended warranties stretching to 15 years or 150,000 miles, and NOx sensor software installed across the fleet to listen for bearings dying in real time. Think about that remedy for a second. The fix wasn't making the engine survivable. It was teaching the car to detect its own death early enough to limp to a dealer. General Motors got its turn in 2025. The 6.2-liter V8 in Silverados, Tahoes, Escalades, and Yukons started throwing connecting rods, sometimes through the side of the block, sometimes at highway speed with under 10,000 miles on the odometer. Nearly 600,000 trucks and SUVs were recalled in the United States, over 700,000 worldwide, after federal investigators started counting the complaints. Root cause, sediment, left from manufacturing and out-of-spec crankshaft machining that the tight, modern clearances and thin oil couldn't shrug off. And the official remedy for trucks that passed inspection tells you everything about this entire era. GM's fix was thicker oil. The company moved the recommended viscosity up a grade, quietly buying back a little of the protection that had been traded away for fuel economy in the first place. Federal regulators later reopened the investigation to ask whether even that was enough. And then there's the one that hurts. Toyota, the company that built the million-mile 22RE, replaced the Tundra's legendarily durable 5.7-liter V8 with a modern 3.4-liter twin-turbo V6. More power, better mileage, exactly what the spreadsheet ordered. Machining debris left inside some engines began destroying main bearings. The recalls started in 2024 at around 100,000 trucks and kept expanding, wave after wave, until more than 270,000 Tundras and Lexus SUVs were caught in the net, with over 70,000 complete engine replacements performed and counting. Toyota, the margin company, even the most conservative engine maker on earth, operating inside the same regulatory box as everyone else, built a hot, dense, hard-working modern engine and discovered that this kind of design forgives nothing. Not a stray metal chip. Not even Toyota's own factory. The quieter consequence is what all of this did to trust. Used car buyers now research engine codes the way they used to research models, because the same truck can carry a bulletproof engine or a ticking one depending on the option box. Databases have sprung up ranking individual engines by federal complaint counts. Dealers run VIN checks specifically to screen out wet belt cars. 2 generations ago, the advice was simple: buy the Toyota. Now the advice is a flowchart. If you wrench on these for a living, or you've had a wet belt apart, or you've run a walnut blaster on a carbon-choked intake. Tell me in the comments where you're working and the worst modern engine failure you've personally seen. The stories from the shop floor are half the reason these videos exist. So, are modern engines simply worse? Here's the honest version. As total machines, modern engines are marvels. Toyota's newest engine family reaches 40% thermal efficiency, 41% in hybrid form, numbers the industry spent decades crawling toward, achieved partly by consolidating around 800 old engine variants down to a couple dozen new ones and perfecting those. Cars are quicker, cleaner, and cheaper to fuel than anything from the golden era, and plenty of modern engines will still see 200,000 miles under disciplined maintenance. The average car on American roads is now over 12 years old, a record which tells you the fleet isn't exactly collapsing. And the Japanese answer to the whole dilemma is hiding in plain sight. The hybrid, where an electric motor absorbs the brutal transient loads and lets the gasoline engine live an easier life near its most efficient operating point. The most reliable modern Toyotas are the ones where the engine works the least, which points to the one lever still in your hands. If the factory won't build the margin in anymore, you supply it yourself. The exact oil specification, not a close enough substitute, changed early instead of at the limit of the printed interval. A minute of warm-up before boost. Fuel that matches the compression ratio. On these engines, maintenance isn't upkeep. It's a structural component the designers assumed would be there, as surely as they assumed the crankshaft would. But the character of reliability changed, and that's the real answer to the question in the title. The old engines were tolerant. They forgave cheap oil, missed services, hard use, and sloppy repairs because the margin absorbed the abuse. The new engines are precise. They reward perfect maintenance and punish everything else because the margin was sold off a percent here and a percent there to buy fuel economy the law demanded. The Japanese engineers never hid any of this. They wrote it into their technical papers, their oil specifications, their dual injection systems, and their conservative tuning wherever regulations left them room to keep some. The reveal was never a secret. It was just published somewhere nobody looks. An engine is a set of promises. The old Japanese engines promised less power than they had, and that gap, that quiet reserve of unused strength, is what your father's truck was spending every time it started on a cold morning. Without complaint, modern engines promise everything they have. Every micron, every gram, every percent, committed. They are more honest machines in a way. They just have nothing left to give you when something goes wrong. If you enjoyed this, tell me in the comments what you want me to cover next. I've got a long list already, but the best ones come from you. Most likes go straight onto it. Subscribe so you're there when it drops.